Good morning, or afternoon, or evening, whatever it happens to be. Today we're going to be talking about section 3.2, which focuses on the correlation coefficient. So, in the last section, section 3.1, our purpose was to learn how to make and interpret scatter plots, and there were three things we had to pay attention to when we were interpreting scatter plots. Those were form, direction, and strength. Form is pretty straightforward. That's what type of shape do you see? Is it a linear pattern? Is it a quadratic pattern? Are there gaps? Are there clusters? Just the shape that you see. Direction is also straightforward because direction is just, is there a positive association? Is the data rising from left to right? Or is there a negative association? Is the data falling from left to right? The one that's more complicated to talk about is strength. Hard to say whether a relationship is strong or not, and a lot of times it really depends on the scale of the scatter plot that you see. That can kind of trick your eyes into saying that a relationship is not strong when it is, or that it isn't strong, or that it is strong when it isn't. So we do have a mathematical way to talk about strength too, and that mathematical way is the correlation coefficient. And the letter that we use to represent the correlation coefficient is r, lowercase r. And what the correlation coefficient does is it measures the scatter about the line. It also tells you about the direction as well as the strength, and I'll show you how, or you'll see that very easily. So I want to just start with two examples. I just pulled these from the internet. I don't know really what that represents. It doesn't matter. What I wanted to show you is when you're talking about the correlation, you always kind of want to visualize a line going through the middle of the data. And it's hard for me to make lines, but there's my best attempt at a line here. And here is my best attempt at a, oh, I'm running too high there. And here's my best attempt at a line here. And I picked these two examples because I think you see that they have different strengths. And strength being the measure of scatter about the line, well, on the left side we see that there's quite a bit of scatter about the line. I mean, not a tremendous amount, but yeah, we do have scatter about the line. And here, if I had drawn a better line in there, we see that, yeah, there is some scatter about the line, but not much. Most of the points are relatively close to the line, meaning in this case that people choose wives that are roughly the same age with predictability here. So we don't have a lot of scatter about this line. So in this picture, we would say that there's a low correlation, so a low value of R, and we'll talk about how to determine those values in a minute. And in this picture, we would say there's a high value of R. So that shows you that we say that the correlation is strong when there's not a lot of scatter about the line, and we say that the correlation is not strong when there is a lot of scatter about the line. So let's look at some facts that you should know about R. The first thing you should know is that R is always a number between -1 and 1. That just tells us that the biggest value a correlation can ever have is 1, and the lowest value that a correlation can ever have is -1. So we're not talking about huge numbers here. They're basically always going to be decimals unless there's a perfect correlation. So what's the difference between the negative correlations and the positive correlations? Well, if R is positive, greater than 0, that means there's a positive association between the variables. So in each of these pictures up here, we would have a positive R value because there's a positive association, meaning that as one variable increases, the other one also tends to increase. If R is a negative value, then there's a negative association between the variables. That would mean as one variable increases, the other tends to decrease. So that's, I think, pretty straightforward. And this is important here. The closer R is to 1, the more perfect the linear relationship. So a perfect R value of 1 would look something like this. With no scatter about the line at all. So that means that all of the points that I drew would lie exactly on the same line. R being -1 would just be the same idea, but our line would be going downward. There'd be a negative association between those variables. And this would be a situation where we would have an R value of -1. So a perfect linear relationship, no scatter about the line, means that you have an R value of 1. What you should note down here is that it only makes sense to talk about R if you're describing linear relationships. If you have a quadratic relationship or an exponential relationship, then R is not an appropriate value to use. It's specifically defined and set up to only tell us about the strength of linear relationships. So always be careful of that. So how do we calculate this value of R? Well, it actually works like this. we take 1 over n minus 1, n minus 1, I guess, for our degrees of freedom there, times the sum of xi minus x bar over the standard deviation of x, and yi minus y bar over the standard deviation of y. A simpler way to say that, actually, you should realize that what we see right here, that's just a z-score, right? X minus x bar over s, that's just a z-score. So that's the z-score for x, and this here is the z-score for y. So what it would mean is we would sum up all of the z-scores for all of the x's in our scatter plot, all the x values in our scatter plot, and we would multiply, that's what's happening between these sums, by the sum of all of the z-scores for all of the y values that we have in our scatter plot, and we would divide that by n minus 1 for degrees of freedom. So we see that the correlation coefficient is an average of the products of the standardized x and y scores. In actuality, so this is a formula that appears on your formula sheet for the AP test, but in actuality you don't use it. If we want to get an R value, we let the calculator compute it for us, which it can do pretty easily. It's not actually something we focus on in this section right now. We're just focusing on understanding and interpreting R, but in section 3.3 we will be asking the calculator to compute some R values for us as well. Our second thing you should know is that R is not resistant to outliers. And that should make sense to you, right? Because the formula is built around means and standard deviations. And neither of those things are resistant to outliers. So something that's built on two things that aren't resistant to outliers, certainly itself is not going to be resistant to outliers. So what that means for us is if we have an outlier in our scatter plot, it's going to change probably change our correlation coefficient a lot. That's something that we need to be careful of and not just put tons of stock into the value of R. We need to first look and see, are there outliers? If there are extreme outliers, does it make sense to remove them before calculating the correlation coefficient? I wanted to show you an example of that here. So we had the scatter plot last time. It showed the state median household income and the state mean household income. And if we just take the data as it is and we crunch the numbers, then we find out that the correlation coefficient's value is 0.634. Again, don't worry about where that came from for now. Just that's the correlation value. So we know that 1 would mean perfectly linear. This is not that, and therefore R is not 1. But there's two outliers here that we should talk about. One is this point here. It doesn't seem to follow that same kind of linear pattern that the rest of the data does, although it does have kind of that funneling out that I talked about yesterday. And this one was also considered an outlier for the purpose of this example. This value right here is Washington, D.C. And the reason why this is Washington, D.C., well, there's a low median household income, so that means most people are poor, which is definitely true in Washington, D.C., but there's a large mean, which means there's a number of rich people who are pulling the mean value up for Washington, D.C. for the mean income, but the fact remains that most people are still relatively poor. So this is D.C., and this is Alaska. Here we have the reverse situation. We have a high median, but a low mean. And my speculation would be because in Alaska, every resident receives a subsidy from the government, that's going to bump all of the median household incomes up a little bit. So these are our two outliers. And if we cut them out of the data set, just pretend that they don't exist, what you see now looking at this picture is that there's a lot less scatter about that line that I drew through the middle. And because there's a lot less scatter about that line, that means there's going to be a higher correlation coefficient. And in fact, if we recompute the correlation, dropping DC and Alaska, we end up with 0.783 as our correlation coefficient. In terms of whole numbers, that doesn't seem like a big difference, 0.634 to 0.783, but considering the fact that for a positive association, the range of values are from 0 to 1, that's a substantial portion. That's like a 15% increase in the correlation coefficient. So we do have to be careful with outliers, and we will get into that in more detail as well later. But there you see that. So what you should be thinking about now is or getting a feeling for is how to talk about R. And here's kind of our guidelines that we'll use. If R is between 0 and 0.2, then we say there's a negligible or slight correlation. So I'm focusing here on positives. All of these words apply if the correlation coefficient has a negative value, but you would just say a negative slight correlation or a negative low correlation. So between 0 and 0.2, we say there's a negligible or slight correlation. Between 0.2 and 0.4, we have a low correlation. Between 0.4 and 0.6, we have a moderate correlation. Between 0.6 and 0.8, we have a moderately strong correlation. And again, like, it depends on where you are in that region. If you're really close to 0.8, then it makes sense to talk with language about a strong correlation. But if you're close to 0.6, then it probably makes more sense to fall in line with the moderately section. So you're kind of, playing it out within that range as well. And if we have a R value between 0.8 and 1, then we say we have a strong relationship between the two variables. Of course, we already mentioned this. If the correlation is exactly 1, then we know it's a perfect linear correlation, that the data points line up in a straight line. So you can always refer back to this chart when you're answering your homework questions and you have to talk about what you see. This is the right language to use. Okay, a few things to take a look at. Our third note is that R alone does not describe a scatter plot. That should make sense to you because we could have a situation where we have a perfect positive correlation. So the data points line up perfectly in a straight line. There's no scatter about the line like this one. But we could also have that same situation here. And there we see that these are two very, very different scatter plots, but they actually have the same correlation value. We say there's a perfect correlation because there's no scatter about the line. The data points would all fall on a straight line. It'd be a different line. That line would have a different slope, but that's something we're going to talk about in section 3.3. When we talk about the correlation, these two pictures have the same correlation. Both have a correlation of 1, a perfect positive linear correlation. I hope that's clear. And we need to look at another situation. I can imagine kind of 3 scenarios where you have a correlation of 0. The first scenario, this might take me a few seconds to build, is the scenario where we have just total random scatter all over the scatter plot here. Everywhere we look, it's just a cluster, a jumble of points. And there, of course, it doesn't make sense to talk about a positive association. It doesn't make sense to talk about a negative association because there isn't an association between x and y. There doesn't appear to be any relationship between those two variables. So that's one obvious situation where we have a correlation coefficient whose value is 0. Another situation where we could have a correlation coefficient whose value is 0, this one maybe is a little weird based upon what I was just talking about, is this one. Here the data points line up in a straight line, so you might be tempted to think that the correlation coefficient would have a value of 1, but that's not the case. Because actually what we see here is that the y values never change. So the y values aren't dependent at all on what the x values are. The y values are just always exactly the same. So when we have a perfect horizontal line, then that's a situation where we also have a 0 correlation, because the question is that the correlation coefficient is answering is there a relationship between x and y? And the answer is no. And y is just always the same. It's unrelated to x. And the third situation where we also would have 0 as our correlation coefficient would be a situation where we don't have a linear association at all. If you take this and you actually find the line of best fit for this graph, it looks like this. It goes straight through. That should be horizontal. But anyway, the point is just to remember our note earlier that the correlation coefficient only describes linear relationships. So this is not a linear relationship, so therefore the correlation coefficient doesn't really apply. We would say that it has a correlation of 0. Okay, so just a few more minutes here. The only way that you're going to get really good with dealing with correlations and making sense of correlations is to practice looking at them and getting a feel for what their values are. So what I have here are 6 different scatter plots, and I've blacked out or grayed out, in this case, the value of their correlation. What I want you to try to do is take a moment, pause the video, and try to guess. What do you think the correlation value is here for each of these scatter plots? When you have your answers jotted down, if you scroll to the next page, you'll find the answers. So pause the video and try that now. Okay, here come the answers. So the first one, we have a correlation of 0. This looks pretty much like random scatter up here. The one to the right, we do have some sort of negative correlation. We would put a line that goes down like this, but there's a lot of scatter about that line, so we know the correlation's value is going to be pretty low, and the actual value is negative 0.3. Here we have a line that would go through the data that would be positive, so we have a positive association, and there's some scatter about the line. We put it right in the middle at 0.5, whereas here we have a positive, oops, way off. Here we have a positive association, and it's pretty tight. Not a lot of scatter about the line, so a strong correlation. Here, including this point at top, we got a negative association. It'd be somewhere in the middle like that. And yeah, pretty good. There's some scatter about the line, but not so much. And here there's almost no scatter about the line. So our correlation would be negative 0.999, negative, because we're going down. Only way you get good at it is to practice. My advice is try this cool website called guessthecorrelation.com. You give yourself a username and you play an arcade-style game where you're guessing correlations and getting points and stuff. I think it's a lot of fun. I enjoyed it. I ended up playing for like half an hour. Reminder, this homework assignment is due on Friday. This part is about the correlation coefficient. The first part is about making and interpreting scatter plots. You will receive a spring break packet also by Friday. So hopefully you understood everything, and good luck.